Okay, but this thing can take 5,000 years. You don't care actually. If you have a very fast machine, it can take, instead of 5,000 years, it can take few months. So it is conceptually simple. However, it has a very high accuracy and details, and it is very expensive. If you're doing something of low intellect, you will have to pay for it. Low intellect means you're doing much the simplest thing. You just discretize Navier-Stokes model and just start to integrate it. So there is no intellectual thing inside. You just discretize some equation and integrate it. So it has a low intellect. That's why you have to pay for this. It requires a lot of computational time. If you hire a stupid worker, you have to pay for it because his stupidity or her stupidity, you will have to pay a price for it. That is low intellect. So low intellect in DNS, it requires a lot of computational time. It requires many millions of CPU hours and also the memory. But in here, as you can see, the power of computation is increasing very, very rapidly thanks to the technology that we have. And you will see the comparison of computation power between 1960s and what you have in here is a CDC 6600, and there back in 1965 it was only the cores that you had was were doing only 10 to the 6 flops. So this is if I'm not right, if I'm not wrong, floating operations per second. Flop means floating operation. Yes, floating point operations per second. It's in here. It was able to do this, but you can see that recently we are getting to into the 16 flops, and it is in the order of petaflops right now, or even right now more than the petaflops. Even the number of cores has increased. So you see that today's actually very not today is very, it's not very updated, but iPhone 8, as you can see, it has 325 gigaflops capability, and the speed of its CPU is 2.4 gigahertz, while the Cray 2, which you see in here, back in 85, it only had 1.9 gigaflops. So you see that the iPhone is approximately 170 times more powerful than the state-of-the-art supercomputer built in 1985, the Cray 2. So today, as we have, it's from November 2020, the Fugaku supercomputer, Japanese supercomputer, is the most powerful supercomputer in the world with nearly 442,000 teraflops. And actually, using these amount of calculations, you can still, still, you are limited to low to moderate Reynolds numbers if you want to do DNS. So we get a lot of data, especially for calibrating RANS type models, as we said, and for some models that we use in larger simulation as well. But for a direct engineering application, we still need to get to higher Reynolds numbers. And Reynolds numbers that are relevant in DNS are still very low for many engineering applications, especially for aerospace applications. And in order to do DNS, you have two ways in order to do uh, direct numerical simulation. What is it? One is to discretize the equation, I mean, Navier-Stokes equations. You can discretize this Navier-Stokes that is written in physical space. So you have your velocity and your pressure, and then you have your x, y, and z coordinates. So you can discretize it and use a finite difference scheme, and you have to estimate these smallest grid size and also smallest time step delta t, and depending on the Kolmogorov scale, and you have to choose the smallest, as I said, time step, depending on the Kolmogorov time scale. And actually, it is very straightforward. You have to simply do the numerical discretization and then integration. The second approach is actually a little bit faster than the first approach in terms of solution. It is to solve the everything not in physical domain, but in frequency domain, that we call it a spectral domain. In a spectral domain, we do not deal with this delta x, delta y, delta z. We deal with wave numbers, okay? Because everything is defined with respect to the scales of eddies. Energy spectrum is defined with respect to wave number and length scale. So if you can somehow convert the original equations, which are written in physical space, to a spectral space, you can actually have much quicker solutions. The problem is this: a spectral approach for solving DNS is limited to only cases where only we have homogeneous turbulence. Okay, so this spectral approach is only for homogeneous. But for all other cases, like in homogeneous turbulence, we have to use the first approach, which is physical discretization. Actually, in homogeneous turbulence is what we have most of the time in many engineering flows. You don't see homogeneous turbulence. Naturally, everything is in a homogeneous. If you have something that causes some asymmetry in the spatial domain, like the walls or solid body, it will generate boundary layer. Then you cannot have homogeneous turbulence anymore, and you have to use finite difference methods that uh, we are not going to talk about this finite difference methods or the simple numerical discretization during this course. Homogeneous turbulence, we said, mostly does not exist in real world. However, we can produce it in the laboratory, and we can simulate it with DNS, and it will provide a lot of information for, as we said, for calibration of RANS type turbulence models. Since one of the main assumptions in many models, in many RANS type models, is to have homogeneous turbulence, so we can use that data. Although it doesn't have direct engineering importance. And as we said, it is beneficial to calibrate the models and have its share in turbulence research. But there are some studies in engineering applications that use DNS as well. For example, this is one study, DNS of turbulence swirling premixed flame in a micro gas turbine combustor. You can read about it. So there are some limited applications in engineering from homogeneous. turbulence. We will mostly concentrate on, as we said, spectral methods. And we will show how life becomes much easier if you write the original partial differential equation sets. Navier-Stokes is partial differential PDE, and it is needed to be discretized in a spectral space. So when you want to do this, you don't have any PDE anymore. So if you take the Navier-Stokes to the spectral space, it won't be a PDE anymore. So it will be it will become a very simple single ordinary differential equation in the spectral space. So as a wrap up, in Navier-Stokes, in DNS, you resolve all the scales. There is no modeling. There is a single realization of the flow. It is conceptually simple. It has a very high accuracy and it has a very high level of description or details. But you have to pay for this, and it is its cost. It's a high cost, limited to low to moderate Reynolds numbers still, and the finite difference method is working for both homogeneous and inhomogeneous turbulence, but the approach of a spectral or pseudo-spectral, which is working on the wave numbers instead of physical space, is only valid for homogeneous turbulence. Okay, do you have any questions? Because from now on, I want to enter to the world of beautiful equations.
I don't have a question.
Okay, spectral method. We have a homogeneous turbulence. Okay, in homogeneous turbulence, there should be no boundaries. As we said, boundaries imply asymmetry, and then it won't be homogeneous anymore. And the solution domain normally is being considered as a cube. You see this cube, and its side length is L. And okay, it has six faces, and you have no solid boundaries. And we have to make sure that the L, this L size, is much larger than the turbulence integral length scale. So what I wrote in here, there is no the L is much larger than the integral length scale, and since it is what you call a spectral method, the equations are not solved in the sense of physical variables like delta x, delta y, delta z, but they are solved after transforming the equations in appropriate form in the spectral space, meaning that we discretize wave numbers. We don't discretize delta x, delta v, delta y, delta z. So frequency of any uh, periodic signal is related to the number of waves of that signal within a certain length, and number of waves is related to the scale information. So instead of discretize the frequencies, we discretize the wave numbers, meaning scales in turbulence. We will see how to do that. So the starting point is to know how to do the transformation of equation sets. What should we understand when we talk about wave numbers, and how does it look like in three dimensions, and how do we actually solve that? Our physical variable, for example, is a velocity field, and it's a vector. So uh, you have a velocity vector field, u hat. It's a function of a space, and it's a function of time. And all the conservation equations, like the mass conservation, momentum conservation, energy conservation, are written in terms of this u tilde. Uh, Again, it is instantaneous velocity field, don't forget. But we don't want to use this u tilde. So we can express it as a summation of wave numbers. And the wave numbers are actually k, summation of wave numbers, this k tilde. And it is a vector in three-dimensional space. So if you use a finite Fourier series, you can actually represent this u tilde as a summation of some wave numbers, right? And this equation is, as I said, finite Fourier series. This is finite Fourier series representation of the original physical velocity vector, u tilde. So basically, if you write conservation equation for u tilde, in that equation, you replace u tilde with something like this that you see. Okay, conservation equation. You remember that you had dui dxi is equal to 0. Okay, so you will replace this ui by this summation sigma of e to the power of ik times x times the Fourier mode, which is u tilde hat. This is called Fourier mode. This part is called the Fourier mode. So I assume that you remember the how to write the Fourier series of a um, function, right? You do remember this from your math. I don't know, was it in your calculus or somewhere else? But you can represent any uh, function, any repeating function as a summation of Fourier series, if I'm not wrong. So this is the actually you will replace, for example, in the continuity, I said this u with this Fourier series, and then you take this derivative of this Fourier series, and then as you see, it's a summation because you have a repeating index, so you will sum up, and the story goes on. So this is the starting point of transferring from physical space to a spectral space. Okay, what is k? K, we said it is a wave number. So first of all, let's take a look at the summation in here. So we have e to the power of ik times x. So k, as you see, is dot producted with x. So you have two vectors, vector of k and vector of x, that is dot producted. So when you dot product two vectors, it will give you one scalar, right? You dot product two vectors. So e to the power of I times k dot x will give you some scalar, and it is a cosine and sine components. You remember e to the I theta was cosine theta minus I times sine theta, right? So it's the Euler. So the equation we obtain is expressed as a Fourier mode, which is a function of wave number. Wave number, it is k, and it depends on the scale, a small and large scale. So it means large and small wave number, and it has time. It has this time. Still, it has its time, and it reflects the evolution in time. So something that is a function of wave number, and it evolves in time. So you have to keep in mind that we are going to solve conservation equation on this cubic domain. So generally, we can represent the wave number vector. We said that it is a vector as 2 pi times n1 over L, n2 over L, and n3 over L. So these are number of waves in direction 1, direction 2, and direction 3. What I'm saying is this. For example, in my solution domain, which is this cube with a side length of L, I could have different eddies in different directions. So I should be flexible enough to incorporate different wave numbers in each direction. And you can generally write this as k0 times n1, n2, and n3, which your k0 is 2 pi over L, and L is this L. So what is 2 pi over L? As you can see, you are using the largest length in this cube. So the largest length actually corresponds to the lowest wave number. Okay? So 2 pi over L is the lowest wave number inside this domain. Are we clear so far?
Yes, hocam.
Okay. So other than k, we had this x in here. So you see the k and you're seeing the x. So x is the physical coordinate, right? And you have the dot product, and let's say you have your k, you have your x. So if you dot product these, you will come up with this thing in here. And then e to the power of I times this thing will give you this. So you know that e to the power of I times 2 pi n1 x1 over L is just cosine of this plus I sine of this. Sorry, it was cosine plus I sine in here. So you can represent this e to the I theta with cosine theta plus I sine theta. So what we are trying to do, as in any Fourier series analysis, we have basically a random field, but it is repeating, right? Which is my velocity field. So the biggest assumption in here is that my velocity repeats itself within that cube. So if this is this cube, if there is a velocity distribution in here, if there is another cube at the left or right or top of this cube or bottom of this cube, it is behaving the same way. So the velocity distribution in all those cubes are the same as in this cube. So uh, these faces are all, let's say, boundaries with repeating characteristics. So I have this velocity and I try to represent this velocity field, which is a random field, with an infinite numbers or infinite collection of sinusoidal functions. Sinusoidal function means waves. So how does a wave number vector look like? That's I told you in here I have an n number of waves in one direction, n2 number of waves in two direction, and n3 number of waves in third direction. What does it mean? So I obtained this figure from Pope's book. Um, if you So in here we are talking about a cube, right? So let's make a story a little bit easy. Let's make it a two-dimensional. Consider you have a square, and this square has side length of L, right? This is L, side length of L in direction x1 and direction x2. And this is your solution domain. So this is a square And this is your solution domain. And within this domain, I want to obtain homogeneous turbulence flow, as I said. So I have this square, and there is a two-dimensional wave that is sweeping this domain, like these waves that are traveling in the ocean. So when you, for example, or in the lake or somewhere. So these are the two-dimensional waves. You remember these from your back in your school even. So I have a square domain. This this is this this is a two-dimensional wave that is traveling, and I can think it is traveling, for example, diagonally, or not completely diagonally, but it is traveling like this. So these are traveling like this, these waves. So from here to here, they are traveling. Okay, uh, I have some unit vector, and I call it unit vector E. And as you can see, the wave number of traveling wave that is sweeping this domain is k. The wave number is k. So the direction of k will be characterized by this unit vector E that I just put it for you. And this is the wave number, k. This is just one example of only one Fourier mode, meaning that if I write k vector for this simple sketch, uh, what are its components? So I have to write components. Let's consider this is x1 direction, uh, and then this is x2 direction. Okay, in x1 direction, what is its component? The question is how many number of waves you can count along x1 direction. So how many number of waves you have in here? You can think of the lines, these lines that you're seeing as crests of the waves. So uh, along x1, along x1, how many wave numbers do I have? I have one, two, three, and four. So four wave numbers I have inside my domain. That's why I write four in here. Okay, on x2 direction, how many wave numbers do I count? This is one wave number, this is two. So I write two. And as I said, because it is written only for 2D domain, I don't have any wave numbers in the third direction. So the distance between these crests, as you can see in here, is 2 pi over magnitude of k, magnitude of the wave number. So this is kind of how you can visualize when I tell you we are solving equations in wave number space. So we represent all scales with many different wave numbers, and in this figure I'm showing you just one of those many. Okay, you see it is a summation of these things. So it is only one of those waves. Basically, we know that the flow is composed of many different wave numbers corresponding to large eddies to smaller scales. So there are many different Fourier modes. And these Fourier modes are all superimposed on top of each other. These are all existing at the same place at the same time simultaneously. So the question is to find the appropriate distribution of Fourier modes that satisfies the continuity and momentum equation. Did you get what I mean?
I'm following and trying to understand.
Okay, okay. I'm trying to find a combination of Fourier modes that can satisfy my equations. What are my equations? Continuity and Navier-Stokes. But those equations have to be also written in wave number space or a spectral space, not in physical space anymore. So The first thing that I can assume to make it simplified is to assume the periodicity, repeating, meaning that I'm hoping that the collection of all these functions will represent real flow field, so I can implement periodic boundary conditions on all faces of that cube. I just talked about it, such that, for example, if there is a cosine wave, it will repeat itself after the domain. So I said that after the domain, I can imagine another domain. So inside that second domain, the velocity will repeat itself. This is periodicity. Actually, an implication of the Fourier series, so is that the turbulent velocity field is periodic. So we have to assume that it is periodic. So accordingly, we can consider the cube that has a size of L in physical space, and we just said that this L is very larger than the turbulent integral length scale. So if it is periodic, then it will be independent of time. Okay? So Fourier representation, you can cancel time from, there is no time in here, there is no time in here because it is periodic. And summation, this is actually the summation over all possible wave number vectors times the Fourier modes that are only a function of the wave number, not time anymore. So these were some basic or fundamentals. So, right now we haven't started transforming equations. Uh, we are defining what wave number generally means and how we should replace the physical parameters. So I
May I
think
ask a question?
yes, yes, ask.
There was a description about Reynolds transport theorem. We are trying to write our equations again from system world to how to say, I don't know, Euler world. But now I guess we are translating our equations again to wave world, right? Or
Yes,
signal
exactly.
world.
You cannot compare it one by one to the Reynolds transport. Reynolds transport was transporting from system to control volume. Okay.
Yes.
Here, yes, you are actually transforming everything from one world to another world. In this manner, yes, that's true. You can see some similarities between Reynolds transport, but don't compare them. Reynolds
Okay.
transport is something else. Yes, you have to uh, transfer from, for example, real world to another world that in that world you are using wave numbers instead of meters and seconds. Okay.
Okay.
Yeah, exactly. Exactly. So right now I just showed you what is the wave number and how you should replace the physical parameters with wave numbers. And next session we will start to implement all these to the equations. Actually, what you will see in the next session is the most important thing, how to transfer the equation itself from my physical world to wave number world.